சரியா கனெக்ட் பண்ணவே இல்லை. லாஸ்ட் டைம் லாஸ்ட் டைம் கூட அவருக்கு தெரியல என்ன பண்ணணும் கனெக்ட் பண்ணாரு. HDMI 7 seconds கழிச்சு தான் டிரெக்ட் ஆகும்.
Yeah, sir, can you make me a co-host from the other ID from where you're not seeing my image?
Currently, there is TOEFL exam today.
Sir, I can't hear you. I think. No, yeah, I've maximized the volume at my end. Yeah, now it's much better.
Can you hear me?
Yeah, but it may be inconvenient for you to.
No. I think they have gone to get the battery for the other mic. Okay.
Okay.
So that is more convenient. Than
Okay.
this.
Okay,
No,
sure.
I mean, I heard at least from a couple of students that there is TOEFL exam today. TOEFL. This people who wish to apply
Okay.
US schools have to take this English exam. Okay.
Yeah. So if you prefer to reschedule it, I am fine with tomorrow.
I think I will base it on, as I told you, there are already a couple of people here and a couple of people online. Okay.
Yeah.
So, but I think now, I used to. Rescheduling is a bit of a nightmare. In the sense, if we don't get something, then a suitable thing that is suitable for all of them, because anytime you get the class is more than 6 or 8 people, it becomes hard to schedule. Okay?
Yeah. True.
Although I have a Friday slot as an alternative slot, but we are hitting that point where all my slack is getting over.
Correct.
Slack in the course, and therefore scheduling their presentations will then become a little problematic.
Correct.
So
yeah, we would like to leave some.
No, I know, but this is one of the basic things, and therefore I am tempted to reschedule it. But I have 2 people here and 2 people online, so I think we should go ahead. Is what I feel.
Sure. Sir, can you make me a co-host in the other one? Oh, yeah. Wait, I will.
Why not?
Wait, I think I should.
You are a co-host, it says.
Yeah, but I wanted to become a co-host. I wanted to share from my other. tablet from where I've joined. So can a co-host make somebody else a co-host?
Other one means what?
So I've joined from 2 devices.
Oh, I see. I didn't notice that. Okay.
Yeah, I'm just checking as a co-host. Can I make the other one a co-host? Okay.
Now,
Yeah, no, but you have made me, so it's okay.
I think now you're co-host on both of them.
Yeah. Which I think helps.
Here's the deal, Madhukar. I think you should go ahead as though you are presenting it normally, okay? Since I will be recording and then I'll be uploading it. I will give them the option. I mean, I would like you to be available if there is enough people who want to, who want some clarifications, etc. Then I will do it on the alternative slot, that is on Friday. Okay.
Yeah.
That's my thing. So, but that is on demand. Okay. So that's optional. So they can come, if they listen to your lecture and then still have doubt, they'll have an opportunity to query you. And that's what I will, I will do. So I don't want to lose a thing. Okay.
Yeah, sure.
I'm going to start recording.
This meeting is being recorded.
Okay, you can make full screen.
Yeah, so that's what I don't know how to make full screen on this one. But is this fine? Is this fine enough? No.
It's a little bit small. It'll be nice if. No. I think it got better. It was something at my end.
Okay.
What? I didn't hear you. Oh, Jessica is? Well, we can't, that's good that she's coming, but I think you should go ahead. Yeah, this is good enough. Yes?
Okay.
Yeah, I have more than the quorum.
Okay. Okay. So I think it's being recorded already, right? So
say that again.
It's being recorded, right?
It is being recorded.
Okay, perfect. Okay, so I think, yeah. So hi everyone. I think you have seen this work on Reluplex, right? So Reluplex is something that I'm assuming that you have seen already. What Reluplex tries to do is to answer this neural network verification problem by transforming into, that verification task into a simplex solving exercise, right? So into a constraint solving exercise, which you can solve using simplex. Okay. So this is what Reluplex tries to do, right? So what is the idea? The idea is that, you have a neural network and there are, the network, of course, takes some inputs, it produces some outputs. And then there is some property that you want your network to satisfy, which is typically encoded as that, for these kind of inputs or for these constraints of inputs, you would want your output to have certain properties or certain constraints, right? And the problem of verifying neural networks is to give a yes/no answer about whether the neural network satisfies this property, that whenever it gets an input which satisfies the precondition, whatever precondition you have listed, then the output of the network satisfies the post condition. Okay, so this is typically, and you may have seen in different contexts earlier also, that a verification query, of this kind is typically this tuple of precondition, post condition, and the system that you're trying to verify, in this case, the neural network.
So why don't you guys ask questions? Okay, yeah, so you can come sit in the front so that I don't have to walk too much. Yeah, I'm just asking them to be props, okay, and
Right.
ask questions.
Yeah. And I think I'm not sure if how frequently I'll be able to read the chat if it does not pop up. It's a good idea to simply stop me and ask questions. It's not necessary that we complete all of it, but it's important that we understand whatever we cover.
So for people on the who are joining online, also, feel free
Yeah, you
to
can simply unmute and ask. Much easier that way. Okay. Okay, so what was I trying to say? I was trying to say that your verification queries typically look like some precondition and some system that you're verifying. In this case, this system is nothing but this neural network that we are trying to verify, and the post condition, right? And you want to establish that whenever this network or this system gets an input which satisfies the precondition, then the output that it produces will satisfy the post condition. Okay. Okay, so okay, so this will satisfy the post condition. And in ReluPlex, we saw one way of doing it, right? So when Sir had presented ReluPlex, sorry, I could not attend that, but I'm sure we would have seen one way of doing it, right? And what was that way of doing it? That way was very simple. We said that, look, I don't know how to address this question, but I know that these are if I have constraints of some form, then I can use simplex on those constraints. And so essentially we said that if we had linear constraints, then we can use the simplex method to solve a bunch of linear constraints. But we don't really have linear constraints, right? So we had non-linear constraints. So then we said that, okay, we'll not worry about non-linear constraints. These non-linear constraints are, even though they are non-linear, they are nice in the sense that they are piecewise linear. So let me look at the pieces separately. So I'll do this bookkeeping exercise where, I will take care of all these linear pieces of this entire nonlinear system. And then I'll query this simplex method, with a linear set of constraints every time. Okay, so this is what we had seen earlier. Okay, now, why are we looking at...
To be more specific, guys, I mean, the way ReluPlex does is it does case splits, okay, then it uses into a bunch of simplex calls, okay. It tries to optimize it, does it in a lazy way, okay. So that much they have understood. So they nod, okay. Yes.
Correct. Yeah. So this is what we were doing earlier, and today we are going to see a way to make this kind of a verification even faster, right? So why is the need to make this faster? Because these neural networks are too big in size, and even if you do case splits of this form, first of all, you may have to do many case splits because there are too many neurons in a DNN, and in anything which is which is of practical interest, there are way too many neurons, way too many layers. And even if you do case splits, you'll have to do too many case splits, and this will end up taking a lot of your time. Okay, so therefore there is a need to make this faster. Okay, so one way of making any such verification exercise faster is to look at what is called abstraction techniques. Okay, so abstraction techniques simply do this. They say that, look, there are parts of the system that I can ignore or I need not focus on, okay, such that I'm still able to do the verification, to verify what I wanted to verify. I'm still able to verify this correctly. Okay, so I want to get rid of certain details about the system which may not be important for the current property at hand. And by getting rid of these details, I'll make my system smaller. Okay, and therefore I'll gain more scalability. Okay, so this is the idea behind any abstraction technique. The whole idea is to get rid of details which are not important, so that you can get a smaller system on which you can run the original technique. Okay, so we'll assume that we are running this original technique of simplex, but we just want to get a smaller network. Okay, now it sounds very nice, but it's a difficult exercise to do. How do we know what is not important, right? It's a very difficult thing, which brings in the other part of this strategy into the picture, right? So there is abstraction refinement. Okay, which says that, look, I don't know what is not important. I don't know what is
Yes, you are.
Yeah, yeah.
You're fine.
Yeah. Okay. So let me assume that, certain things are not important. Let me just try to, just say that, look, these things are not important. A bunch of things here are not important. So I'll just make a guess on what is not important. And then if I somehow realize that I may have deleted too much or I may have lost too much information, then I'll try to bring some of this back by a refinement procedure. Okay. So this is what abstraction refinement basically means. Okay, so this paper, which is a CAV 2020 paper. CAV is a very well-known, very reputed conference in this area, in the area of verification in general. Okay, not exactly neural networks, but it covers neural networks also. Okay, so this is a CAV 2020 paper on abstraction-based framework for neural network verification. So the idea is very clear, right? So we'll try to make the network smaller, so that our verification query, which we were doing earlier for Reluplex, can now be done on this smaller network. The rest of the verification remains the same. It's just that we are trying to get rid of certain parts of the network by trying to make this network smaller. And if we realize that the verification query succeeds, we'll be done with it. If we say that there is a need to bring some of the information back into the system, we'll bring it back into the system. This is what we are trying to do today. Okay. I think this is some general motivation on DNNs, which is not relevant in this case because we have been doing this course, so we have looked at such motivation a lot of times. The slides have been made in such a way that even a standalone talk on this topic can be given. But the general motivation, I believe, is not needed. Anyway, I'm just saying that DNNs are everywhere these days, and it's easier to create than handcrafting software. Sometimes it's easier to create a software which has certain machine learning components because it may be difficult to formalize that logic or formalize some parts of the logic, which is easier done by training a system on some existing data. Okay, so this is, and again, this is an example which once again you may have seen earlier. This is an airborne collision avoidance system. This was developed in response to mid-air collisions between commercial aircrafts. And earlier, this used to be done by a lookup table. So the idea is very simple here. There is some aircraft which is going in some direction with some velocity and so on. And if there is an intruder aircraft that comes, then what should this own ship do? Should it continue to go in its current line of motion? Should it deflect left, right, or sharply to the left or sharply to the right? And this sort of a thing can be done by creating a lookup table where you try and see what are the sensor inputs at some point in time. And if you realize that there is a network which is at this point and there's an intruder which is very close to it, then the network should there's an aircraft which is at this point and there's an intruder which is very close to it, then the aircraft maybe should go somewhere. Okay, so this can be done with a lookup table, but this takes too much space, and DNNs in this case at least they were very successful. It could be done as compared to a size of 2 GB, which was taken by the lookup table. This could be done in less than 3 MB of memory. Okay. Okay, again, this is some explanation on, some motivation on why this is important. We know why this is important because neural networks, when you make a small change to the input, which you believe may be harmless, but that's not exactly true about neural networks because we don't understand what's going on inside a network. There are too many weights and biases and all these numbers and too many connections. So we don't really know what is happening. So sometimes what happens is that, if by making a small change in the input, which you believe should be harmless, the output changes by a great deal, and we don't want such things, especially when they are not desirable. Okay, so we use neural network verification to prove this thing. Okay, so one of the things which is important and which I'm not sure if it was covered in the last lecture is this is a hard problem in general. Okay, it becomes exponentially more difficult as the network size increases, and this is something that I would urge you to look at. So this is in the appendix of the Reluplex paper where they prove that this is NP hard. Okay. So this is something that I motivate you to look at. Okay. Okay. But we'll in this lecture, we'll assume that, this is a hard problem, and therefore we are trying to look at an abstraction refinement technique. Okay. Therefore, I mean, so why should we reduce the size of the network? Because it's difficult to verify a network which is too big in size. Okay. So here is the one slide summary of what happens typically in these cases, right? So, and this is not a new thing. It's a well-known story in formal verification. In fact, this paper also uses the same story, just that they provide a framework in which this can be done. The contribution of this paper is not the technique of abstraction refinement, but a framework in which this can be done for neural networks, right? But the idea, as I was saying, it's a well-known thing that you replace your system by a smaller or an abstract system, right? So we'll replace our network by a smaller network. Okay, I've denoted this by this n bar here. Okay. Now, the way we'll do this is that by construction, if our n bar satisfies the specification, then n will also satisfy the specification. So this is something that we'll enforce by construction. Okay. Okay. Why? Because how can we do this? Because we are the ones who are creating this, right? We are the ones who are creating this smaller network. So this is something that we'll do by construction.
Yeah, here okay. I just want to, since we have discussed in the class the notion of over approximation and under approximation. So, the point that Madhukar is making here is that the n bar is by construction and over approximations. And that's why if whenever you prove a property for n bar, it'll also hold good on n, and that's done by constructions. That's the point he's making. Okay, go ahead. I just wanted to reemphasize. That notion that they have already, been introduced, and they're also working on an assignment in which will drill. Hopefully, some problems it'll drill them that concept down well. Okay, go ahead. Yeah.
Certainly. Yeah. So this is exactly true of any over approximation that you do. That if you have built an over approximation, then in general, when you are building an over approximation, you are trying to add more behaviors than what the original system can have. And therefore, if the property holds in this new system, which has all the original behavior plus some new extra behavior, so then the property must hold in the original system, which is the argument that Sir was making. And since you know this already, I'll not spend more time on it. But this is, just to say this once again, that this is happening by construction. Okay. Okay. So if n bar meets the specification, then n also meets the specification, which is what we are trying to prove, that n meets the specification. This is the desired work. Okay. Now, if n bar fails to meet the specification, whenever we fail to meet a specification, there is typically a counter example. Okay. So this failure to meet something, this failure to meet the specification, there is a witness to this kind of a failure. Okay. And this witness is typically called a counterexample. Okay. So what does this look like? This looks like that, what is our specification? Remember that, we are saying that, we have some precondition, we have some input which satisfies the precondition, we have some network, and we have some post condition. And we are saying that, look, in this case, n bar here, and we are saying that n bar fails to meet the specification, which means that, we are able to find an input which satisfies the precondition such that its corresponding output does not satisfy the post condition. Okay. So this failure to meet this specification says that I'm able to find such an xin. Okay. And this xin is what I'm referring to as the witness. Okay. This failure is nothing but the existence of such a witness. And typically in verification, when this witness exists, we are able to get this, okay, in such verification queries. Okay. This, I'll tell you, how this happens, but this is available to us. This witness is available to us as a counterexample. Okay, and it is this counterexample which tells us whether our abstraction was too coarse, whether we left too many details out of the system, or how can we get some of it back, and so on, right? So this thing is typically called a CGAR, a counterexample guided abstraction refinement. So we know under abstraction, we know refinement. If the refinement is guided by this counterexample, then this is called counterexample guided abstraction. Okay, and this is a very popular way of doing refinements.
Yeah. So is this clear? I mean, yeah. So because the counterexample is on n bar, it could be spurious. Okay. Yeah. Okay. Okay. Yeah. You can go ahead.
Correct. Yeah. So I'll revisit some of this later. Yeah. Okay. Now, okay. In fact, right here, in this case. Okay. So there must be. So if n bar fails to meet the specification, this failure, as I was saying, it can be seen as a witness, which is also termed as a counterexample here. So we'll use this counterexample. Now, whenever we get a counterexample, right? So focus on this part of the slide. So we are saying that we have this n bar here, and we had found an input which satisfied the precondition, but the corresponding output did not satisfy the post condition. Okay. Now, remember that this n bar is something that we have constructed. Okay, this is not our original system. Okay, so the failure of xin or this xin witness, the xin is a witness to this network not satisfying the property. But we are not interested in some input for which n bar does not satisfy the property. We eventually want to only take those inputs into consideration for which n also does not satisfy the property. Okay, so we can check this, right? Now that we have an input, we can simply feed it to n and check if the output, if x out with respect to n and not n bar, if this satisfies the property. If this satisfies the property, we know that this is what is called a spurious counterexample. Okay, because it looks like a counterexample in the abstract case, but it is not exactly a counterexample when you come to the original case or the concrete case. Okay, this is a spurious counterexample. Okay. Okay. So the point is that if it is not a spurious counterexample, then you know that n violates the specification. Okay, so if it is not a spurious counterexample, then you know that you have found a violation. Okay, your only problem is that if the counterexample turned out to be spurious, then you don't know. Okay, but if it was actually a valid counterexample, then in the original network you have found this input, the same input again, such that the corresponding output does not satisfy the property. Okay. So there are two cases, right? You either find a spurious counterexample or a real counterexample, right? So I'm just to distinguish this other kind of counterexample, I'll call them real counterexamples. So you have either found a real counterexample or a spurious counterexample. If you have found a real counterexample, you're done. Okay, your system does not satisfy the property, and to prove this to somebody, you have also got a witness. xin is your witness. Okay. When you get a spurious counterexample, there is something wrong with your abstraction. Okay, in which case we need to refine. Okay, so this is what we do. Okay, and this is the abstraction refinement procedure in general. Okay, you make the system smaller. If the verification succeeds, you are done. If the verification does not succeed, you get a counterexample. That counterexample can either be real or spurious. If it is real, again you are done. If it is spurious, you refine your system. And then the whole thing starts all over again. Okay, this is this abstraction refinement loop to make any verification query faster. Okay, there are details to it which we have missed. How do you abstract? How do you refine? I mean, how do you look at this spurious counterexample? What do you do? What exactly? So all these details is what we'll focus on for the rest of the talk. But this is the general idea. This is the overall idea. Any questions till this point?
Yeah. So can you explain what are spurious counterexamples once again? I didn't understand it properly.
Okay. So what are we saying? We are saying that. Okay. So suppose. Okay. So let me get rid of this.
Yeah, in simple term, who asked this question? Can you identify yourself?
From Shantanu.
Shantan. So one way, maybe, one way I would define is, so a spurious counterexample is one which fails to satisfy the property on n bar, but it succeeds for the same inputs. The property is satisfied by n. Okay, such a counter example is called spurious.
Yeah. So yeah,
it
exactly
succeeds.
right.
I mean, it fails on n bar, but succeeds on n. Is that clear?
And in real counterexample, it is the opposite, is it?
A real counter example is one which fails both on n bar and n.
Oh, I see. Okay, got it.
So that's when a real counter example gives you the bug, is an actual bug on your original system as well.
I see. Got it. Yeah.
Correct. Okay. Okay, so we'll continue.
Yeah, please. Yeah.
Yeah, so this is again some background.
You can skip these slides.
Yeah. Skip these
And
slides.
they have actually seen this particular example as well.
Correct. Yeah, you would have seen this example.
Maybe you can explain it here. I mean, if indeed you're going to be using this the same thing. Yeah.
I'll just use the setup. So let me just, So this is, anyway, so what I was saying is that, so your verification query is typically of this form. So you have a precondition, postcondition, and a network. And here is an example where, you can, so I can ask that, is there, or is it possible that output is less than input for any input? Okay, so I can ask such questions, right? Is it possible to find an input such that its corresponding output, input in, such that its corresponding output out is related by this output is, sorry. Can we find this? Okay. These are the kind of questions that I'm interested in. And as sir was saying, you have looked at such examples earlier, so I will not. Okay. I think one of the examples in this paper was that is it possible for this one to be in 0.5 such that this is in 0.51, something like that. You can say that, can you find an input which satisfies this condition?
Yes. This example, I've discussed this particular thing. Yeah.
Correct. Yeah. And in this case, it turns out that this is actually, this is true. In fact, for input is 0.5, the output will be the same as input. So this will also be 0.5. But since you have seen all this, we'll not spend time here. Okay, this is just some examples. Okay. Now, this paper, okay, so this is the general, so far whatever we have spoken about, this is the general problem of verification, in case of neural networks, right? Is there some precondition, is there some postcondition, the network is there, everything is in its complete generality, right? But we'll make certain assumptions before we proceed, okay? So there are some assumptions that we'll make here. The first is the assumption on the network. So we'll assume that we are talking about neurons where ReLU is the only activation function. Okay, and we'll further assume that there is a single output node. Okay, so this is just an assumption on the network. Our networks will look like this. Every time there's an activation function, it's going to be ReLU, and there's going to be a single neuron in the output layer, which will be the single output node. Okay, this is the assumption on network. There's also an assumption on the precondition, which says that we'll only put conjunctions of linear constraints on input values. Okay, we'll just use linear constraints on input values. Okay, these are some assumptions on the network, on the precondition and the network. And the post condition says that we are only interested in checking a post condition of this form, whether y which is our output node, whether the value of y is bigger than some constant c. Okay, so we are interested in verification queries which have this form. Okay, it may appear very limited, that you can only do very limited kind of verification queries if you have to put in all these restrictions, but it's not as limited as it may seem, and we'll come back to this. Let's for now let's
Just to interject here. So while Madhukar will explain, this may not be as limiting. Now, for example, if you're doing Z3 or reluplex, it allows you to, it is not limited. The constraints are not of the precondition or the postcondition, not limited to be of this form. It can be arbitrary Boolean combinations of conjunction of linear inequalities. Okay, so that's why he's saying that it is. So it is this restricting. At least it restricts in principle, but there are ways of. Yeah, go ahead. Yes.
correct. Yeah. So you're saying there are ways to.
They've already seen as far as Z3. So they've seen Z3. DNN verification with Z3 is DNN verification with reluplex. Okay, so that's why in that context.
Yeah.
Doing this context. Go ahead.
Correct. Yeah. Certainly. So that's what. So we have put some restrictions. We have said that the network will have only one neuron in the output layer, and we'll only be checking things of the form y greater than c. We cannot check any other things and so on. But we'll not worry too much about it. This itself will allow us to do a lot of very interesting properties, and some can be transformed into this form, which we'll see later. Okay. Now, here is what the authors of this paper propose to do. Okay, they say that we will transform this network n, which is our original network, into this n bar, right, which will be our abstract network. Whenever we are doing this transformation, we will ensure that for any input x, remember that there is only one output neuron, right? So I can talk about nx. Nx is the value at the output neuron when x is given as an input to the network n. Okay, so this is the value of y. Y was our output neuron. Okay, so what are we saying? We are saying that whenever we do this transformation, we'll ensure that this transformed network, we have this original network and we are creating this transformed network. We'll say that, look, we'll be making some changes here so that we get our transformed network. So whenever we have any transformed network, we'll ensure that the value that it is computing for any input is bigger than the corresponding value that this original guy is computing for that input. Okay, this will always be bigger. Okay, this is something that we'll ensure. I talked about ensuring this as part of our construction, right? So this is what we'll ensure as part of our construction. Okay. Now, assuming that we have ensured this, assuming that we have created this, every time we create this is guaranteed that that the abstract network will compute a bigger value at the output than the original network. Okay. Now, if the abstract network tells me that the property holds, which is what I mean by safe here, that the property holds. Okay. Remember, what is the property? The property is that y is less than c. Sorry.
Y is greater than c. No?
Y is greater than c. Okay, so we want to check, is it possible that y is greater than c? Is this possible? Okay.
Yeah, I mean, the question here is, what is the property? Okay, so your property is, you want to check if y is less than or equal to c.
Correct. So the property, so see here is, so the
or you could say that you want to check, the property might be y is greater than c, but
y
you want
is
to
less
check
than
the
equal
violation. Okay, which is y is less than or
the
equal to c.
property is this, the post condition, which is typically the negation of the property, okay, is y greater than c. Is this fine? The property is that y has to be less than equal to c. This is the post condition. So here we had put a restriction on the post condition Q. Okay.
Yeah. So I think okay. So let me make this correction. See, we have defined in a normal definition of post condition is the actual property itself.
Correct. Okay.
So
It's okay. I'll explain.
use that. So the property, the post condition, because pre and post when you look at programs, yeah. So I don't want to dwell on that. So what it means
So I'll just clarify this.
is normally when you check in Z3, if you want to check a certain property, you take the negation and then check if it is unsat. No. Okay.
Correct.
Yeah, you want to check the validity of the property. So for which you want to check if the negation is satisfiable.
Correct. So you want to check that the property is valid. And instead of checking for validity, you check that the negation of the property is satisfiable. Because if the negation of the property, so property is valid means that the negation should be unsatisfiable. But if the negation turns out to be satisfiable, then you know that the property is not valid. Okay, that's why you negate it and then check for satisfiability. So this post condition is what you check the satisfiability of. You check whether it is possible. The property is something that you always want to hold, right? I mean, you say that, this should always hold. Now, you cannot, you cannot ask that, does this always hold?
Yeah. So let's for the purpose of this lecture, Madhukar, if it's okay, let's call the post condition as verification condition. Okay. So because the post condition is technically used in the context of OR logic as something that you want to actually check the validity of. Okay. So he's using it slightly differently. Okay. So let's not.
Yeah. Okay. Yeah. But it's important to understand that we are talking about the same thing. Okay. We want the property to always hold. So we are checking whether, there exists an instance such that the property does not hold. Okay. This is the duality between satisfiability and validity. It does not have to do anything with what we call property, what we call post condition, this is just the duality between satisfiability and validity. We want to check that something is valid. We are just checking that the negation of it is not satisfiable. Is that fine? Does that make sense?
Yeah, I think that's fine. Yeah.
Oh, okay, sure. Okay. So if the abstraction is safe, which means that, if this holds, then we know that the concrete is also safe, right? Why? Because if n bar of x is less than equal to c, then n bar of x is remember that is the bigger one. Between n of x and n bar of x is the bigger one. So if the bigger one itself is smaller than c, then the smaller one is definitely smaller than or equal to c. Okay. So then this is, remember that, this is what we wanted to, to enforce. And by ensuring that our construction gives us this, which we'll see how, we have ensured that this makes sense, right? So this is the kind of abstraction that we'll be doing. Whenever we abstract, we'll generate an abstract network and we'll ensure that this abstract network computes a bigger value at the output neuron. We have only one output neuron. At that neuron, we want to compute a bigger value than what the original was computing. That's all. Okay. This is what we want our abstraction to satisfy. Okay. But how will we actually do this, right? How will we do this transformation, right? How will we do this transformation? So we'll do this transformation by actually merging neurons. Okay. This is the step that we'll do. Our step, to achieve this transformation will be take two neurons and merge them. Okay. Which will create our abstraction. And while merging, I just have to ensure that, the output gets bigger and bigger than the output of the original network. Okay? This is all that we want to do.
Not only that, because your abstraction, sometimes you want it to be smaller neural network. Okay, so that
correct. Yeah, which
be more efficient.
Correct. It's a very valid point. Yeah, thank you, sir. So what we are saying is that we want a smaller network, right? I mean, the whole exercise of this abstraction is to be able to check an abstract network faster than checking the original network, right? So if you get a bigger abstract network, then what use is that? Okay, so this merging of neurons will give us that also. Hopefully, when we merge two neurons into one, hopefully the network will become smaller, right? Because the network is composed of these neurons and these connections between neurons. If we have fewer neurons, then there'll be fewer neurons and fewer connections. So hopefully the network will be smaller. So this merging seems to be doing it for these guys, and this is what we'll see how in okay. But one thing that they have proposed is that they don't do this, they don't start this merging right away on this network, and first they do certain changes on n to make it ready for merging, and then they start the merging. Okay, so let's see what are the changes that they do. Okay, so here are the changes that they do. They first transform this n into n bar, n prime, and then this n prime into n double prime. Okay, these are the changes that they do, and the merging that we had said we will not do here, but we'll do here. So this is where we'll start merging. So merging is still one slide away from us. Okay, right now we are just doing this transformation. Okay, so here is the transformation. Okay, so they take the network. So this is what your network looks like, right? I mean, pick any of these examples. Okay, so there are some neurons, there are some connections, there is one output neuron, there are some input neurons, and then there are some hidden layer neurons, right? So this is what our network looks like. Okay, now before they start merging, they want to classify every neuron as either positive or negative, and then again every neuron as either increment or decrement. Okay, so they want to mark every neuron. This is a positive neuron, this is a negative neuron, this is an increment neuron, this is a decrement neuron. So they want to do this kind of a marking. Okay, so let's first understand what this marking is, and then we'll see how it is done. Okay, so the positive marking means that the outgoing edges of that neuron which is marked positive will only have positive weights. Okay, so this marking is for outgoing edges. Positive, negative marking is based on the weights of outgoing edges. So if all the outgoing edges are positive weight, then it will be a positive neuron. If all the outgoing edges are negative weight, then it will be a negative neuron. If there are some output edges which are positive weight while some other which are negative weight, then we create two copies of this. So this is split into two copies for this neuron. So this n neuron becomes n1, n2, or n pos and n neg in this case. And we retain the positive arrow on the positive side and retain the negative arrow on the negative. Okay, all the incoming to this, of course, have to be copied to everything here and here. Okay, why should the incoming be copied? So that this continues to get the same value from the input. Whatever value was coming here should continue to come till this point. Similarly for this one, right? Whatever value it was getting earlier, it should continue to get that value. So therefore, all the incoming has to be copied. Okay, so we are just trying to say that, look, here is something that I wanted to mark as positive or negative. This was not clearly positive or clearly negative. Let me create two copies and then mark one as positive, one as negative, and I'll retain edges of only one kind in either one. Okay, this is a very simple thing. It's just that, it increases some burden for you. You have to now keep two copies and so on, right? And this, remember that this one had two copies, and then, some other layer also maybe more copies and more copies and more copies, but it's okay. In the worst case, every neuron will get split into a positive part and a negative part, right? So in general, this is a 2 times increase, right, in the number of neurons. Okay, so this is positive or negative classification. Is this fine? Any questions till this point? I think it's important to resolve these questions.
Is that clear?
Yeah.
Okay. Yeah. So just to give you an example, see that here there were this one had a 2, a 1, and a -3 coming out of it. This is 2, this is 1, and this is -3. And if you notice here, we have kept 2 and 1 on one side. This is the positive part, which is denoted by this plus here. Okay, it may not be very clearly visible, but this is the plus here. And this is the negative part.
It's quite visible with this expansion.
Okay, yeah. So this is the negative part, which has the -1, which has the -3 thing. So this is just to show that, look, this is exactly what they're doing. You know, what I said was what is exactly being done. Okay. So this is a positive negative split. We understand this positive negative split. Okay. So now we'll get rid of it.
So why are we splitting?
We'll come back to why they are splitting. We'll just first understand the equivalence. That if you split, you get an equivalent network. Is the equivalence clear? Forget the reason, but is the equivalence clear?
Sayantan, you asked the question. So is the
It's clear.
yeah. I mean, eventually, this is a intermediate step towards, like Madhukar mentioned in the earlier slide. These are intermediate steps that are used to eventually construct an over approximation for the kind of property that less than or equal to a constant property purely by merging nodes. Okay, and this is the first kind of transformation step that is used to classify these all intermediate nodes as either positive or negative.
Yeah. Okay. So this is okay. So this is what we are doing, right? So we are, I mean, the general point is that, you know, we are trying to make it merging ready, right? We want to do some merging, but we believe that it is not yet ready for merging. So let me do some equivalent transformations such that I get an equivalent network which is merging ready in some sense, right? And we'll see the motivation behind, you know, why was it not merging ready? Why is it now merging ready, and so on. Okay. So we have done one transformation. Now the other transformation, which is also very important, is classify every neuron as an increment or a decrement neuron. So when is a neuron an increment neuron? An increment neuron, a neuron is an increment neuron if increasing its value. See, we are talking about some neuron n. So this is an increment neuron if increasing the value increases the output value.
You mean increasing the inputs?
Correct. Increasing the value of this neuron. Any neuron is an increment neuron if increasing the value of that particular neuron, which we are going to mark as increment. So n is an increment neuron if increasing the value of n increases the value of y. Y is our output
of the eventual output. So when you say the value of a neuron here, you're defining it as its output. Okay.
Correct.
Yeah, the value of a neuron is considered as its output. So whenever you increase, I'm just trying to understand myself, Madhukar, by asking a rhetorical question. So if the value of the output of that neuron increases, then the eventual output of the entire network increases.
Yeah. Okay. So n is an increment neuron if increasing the value of n increases the output. N is a decrement neuron if decreasing the value of n increases the output. Remember that the output must always increase. This here I don't have two arrows. Here I just have one arrow. This must go up. Now this can go up by either pushing this up or pushing this down. But this must go up. I always want my output to go up. Okay. This is how I want our construction to be. So I just want my output to go up every time. Okay. Now there are two ways I propose this can be done. One is that I pick a neuron. I either increase its value to see an increase later or decrease its value to see an increase later. Okay. And it is based on this that I'll start marking as increment and decrement. Okay. So let's see how this can be done. Okay. So why I claim is an increment neuron? Why is an increment neuron? Because increasing the value of y increases the value of y. Okay, any n is an increment neuron if increasing the value of n increases the value of y. Y by definition is an increment neuron. Is this fine?
Is that clear? So how about Guhan? Are you there?
Yes, sir, Ramin.
Okay, yeah. So that's the trivial case because
That's the trivial case.
Y itself is the output node.
Okay, and I want to say that if increasing the value of any neuron increases the output, then I will call that as increment. Y, of course, is an increment neuron because increasing the value of y increases the value of y. Okay, it's a trivial statement, but anyway. Okay, so this is an increment neuron. Okay. Now, I claim that this neuron is an increment neuron. Why? Because if I increase the value here, then the value that I'll get here is 3 times that value. So one way for me to increase this y is to increase this value, because if I increase this value, more value will flow across this edge, and if more value will flow across this positive weight edge, then I'll get more value here.
Yeah, that's because green means positive.
Yeah, green is used to represent positive here, and red is used to represent negative. Right?
Because all its output weights are positive, so it's always increases its output. So
yeah. Okay. So this is green, and this is also green, right? So we have.
No. Okay. There is a question here.
Yeah.
Jessica.
So what if it has a ReLU at that neuron, like after? Yeah, it won't be increasing, right? If it gets like a negative number, then it's always 0 or something.
Correct. But if I increase it, I mean, see, the ReLU may decrease it, but if I increase it, the value at y cannot decrease, right?
Okay. Yeah.
Okay. So think of this in that sense that increasing it only increase the value of y.
Yeah.
Okay. It may not increase it in every case, as rightly pointed out by you. That if this value was -2 and I increased it to -1, how does it matter? It'll anyway get 0 here, right? That's fine. Let's not worry about it. But we know that it's not going to decrease anyway, right? This will continue to be bigger than or equal to. Okay. The abstract will continue to get a bigger than or equal to value, right? So we are,
because the output of ReLU is always going to be greater than or equal to 0 anyway.
Correct. Yeah. Okay. So this is fine, right? Now this is an increment thing, and similarly, this is a decrement neuron. So I claim that this red guy here is rightly colored red. It's a decrement neuron. Why? Because this is connected to a green neuron by a negative weightage. Okay. So this guy has to increase. This guy is sending an edge of weight -1 to this guy. So this guy must decrease, right? I mean, if it increases, then more negative will come at y, which we don't want. Right? We want y to increase. So if we want y to increase, then we would ideally want this to decrease. Because if this decreases, then because of this negated weight here, the effect will flip. Okay. So this is the idea, except that we'll do it in the backward direction. So we'll color this green. And now if we go back along a positive weightage, so you can think of this, that you're trying to do this coloring in this direction. You start with coloring this as green, and then when you go back along a positive weightage, you color it green. If you go back along a negative weightage, you color it red. Correct? And here is the motivation behind splitting positive negative, that you will not go to the same neuron once with a positive weightage and once along a negative weightage. Okay? Because no neuron has a positive and a negative outgoing. So this is just to ensure that this coloring is being done in an appropriate way. Okay? There are ways in which this coloring can also be improved, but we'll just understand the paper as it is. Okay. So this is the reason why, there was a question, right? Why are we splitting? This is the reason why we are splitting. So that when we go back, when we are trying to do this in the backward direction, we don't have to worry about getting conflicting colors at a node, because that node is also reachable along a negative weightage and also along a positive weightage. There are no such nodes which have both negative and positive going out of them. Every node has either only positive going out of them or only negative going out of them. So we are not going to land in any conflict with respect to this sort of a coloring, okay, which was the motivation behind keeping them as positive.
Sayantan, you had that question. Is that clear to you now?
Yes, it's clear. No, I have one more question now. So, so from V11 we are going to V22 with 1, right? So this is positive, but V11 we are coloring it with red. Why is that?
Correct. So remember that, notice that the color flips, right? So when you go back along a positive weightage, you copy the color, but you flip it, right?
Yes.
So if this has to decrease, this must also decrease.
Oh, I see.
Correct?
I see.
Okay.
Yes.
So the green is preserved along a positive, red is preserved along a positive, but it flips in case of negative. So it was not going to red because of this thing. It was flipping because of that thing. The effect really flips. Is that clear?
Yes.
Okay. So that is all that is there to this paper. Okay. This paper says this, right? This is the crux of their idea. Now we'll just complete. Anybody has any question? This is the point to ask.
In your
Yeah.
So in the two diagrams on screen, if you consider the left one,
Correct.
So V11 plus.
Correct.
If we approach it from V21 plus,
Correct.
we'd assign green red.
Correct.
But if you approach it from V22 minus,
Correct.
We'd assign red.
Correct. And that's exactly when we split, like how we were doing in case of positive and negative. If something was not purely positive or purely negative, we were splitting. In this case also, if something is not purely green or purely red, we will split. I was about to come to this. Yeah, sorry. And thanks for bringing this up. Split if needed. Does that answer your question and also clarify it for others?
Is that clear? Yeah.
Okay. People attending in person and online, everybody?
Yes.
Okay, perfect. Okay, so now we have the required setup to continue. Okay.
So can you give an example of where you split? The second case of
It is
split?
exactly in this case. It is exactly in this case. And I'll just unclutter to show that it is being split.
Yeah, I mean, if you could blow it and then explain it just once more. So
Yeah. See, this is the neuron that was being talked about. This is the neuron that was there in the question just now. Saying that this neuron, because it is connected from a green by a positive weightage of 2, it should remain green. But it's also connected from a red by a positive weightage of 1
to a pink.
Red.
So that's
And
when
that's why there is a V11 plus green and a V11 plus red, which has also been marked as an I and a D for increment decrement.
Yeah.
Okay. Notice that this 2 is now being split here. This 1 is, the connections have been separated. Is this fine? This is exactly that example.
Yeah, no questions here in the physical, here in the auditorium. Is there any question either by Guhan or Sayantan? Okay, we can move ahead.
Okay, perfect. Yeah.
By the way, Madhukar, we have a hard stop because there's leaves at 5. So 5:55 is the hard stop. Now, even if you go at your own pace, okay?
Correct.
But even if there is something left over, you can always finish it up on Thursday. Okay.
Certainly. Okay. So this is fine, right? So what is it that?
And this thing, because they will be using Marabu.
Yeah.
Says right now they are doing. I mean, they will have an assignment. Same thing. Now they're doing an assignment of verification of a DNN using Z3. Okay.
Correct.
I'm going to be having them do hopefully the same or something, on Reluplex and this Marabu with node merging. Okay. So they better understand this, carefully and thoroughly. Yeah. Go ahead.
Okay. Sure. So what we have done by this kind of a splitting, we have, first of all, we have created an equivalent network. Secondly, we have ensured that, our neurons are now all marked, right? They are either marked as positive or negative, increment, decrement, both. Every neuron is marked as both one of positive, negative, and either increment or decrement. Every neuron is marked in this way, either positive or negative, and either increment or decrement. Okay, so this marking has been done, and this marking does not disturb the network in any way, except that it makes it bigger. By how much bigger? Every neuron can be split twice when you're doing positive, can be split once when you're doing positive negative marking, and then every neuron can be split once when you're doing the increment decrement marking. Okay, so in the worst case, you can get 4 times. The network can become double in the first marking and 4 times the original in the second marking. Okay, in the worst case, you may not have to split everything, but just in case. Okay. Now, here is what they propose, and this is their proposition. Okay, this is the framework that they have proposed. They said that look at, so one of the things that they say is that look, when we are merging, remember that, how are we abstracting? We are abstracting by taking 2 neurons and merging them. Okay, so they say that if I merge 2 neurons, they have to be in the same layer. Okay, that's the first thing which is important to understand. We will only merge things which are there in the same layer. Okay, I will take 2 neurons in the same layer and merge them. Okay, the other condition is that they must agree on their markings. Okay, and when I say agree on their markings, both the markings. So a pause ink neuron can be merged with another pause ink neuron. A neg dec neuron can be merged with another neg dec neuron. A pause dec neuron can be merged with another pause dec neuron, and a neg inc neuron can be merged with another neg inc neuron. Okay, you can pick any 2 neurons if they agree on both the markings and if they are in the same layer, and merge them. Okay, so merging is this process of keeping just one, combining them into one neuron, right? So when you combine them into one neuron, there are things that you have to worry about, right? The incoming edges, that suppose I'm combining these 2 into one neurons, right? Now if this is a neuron which was sending an incoming edge here and an incoming edge here, now if these have been merged, there cannot be 2 incoming edges, right? So we have to somehow combine them into one. Okay, similarly for an outgoing edge, if this had an outgoing here and this had an outgoing here, we cannot have 2 outgoing edges from one neuron, so we have to combine this also into one. Somehow we have to do something so that we combine this into one. This is the entire process of merging and abstraction. Pick 2 neurons which agree on the markings, which are in the same layer. Okay, and then do something about the incoming, do something about the outgoing, so that you don't have multi-edges coming this way and multi-edges going out. Okay, now here is what we do. If we are merging 2 positive increment neurons or 2 negative increment neurons, okay, so it doesn't matter whether positive or negative. So if you are merging 2 increment neurons, if 2 increment, and they can only be merged if they agree on all 4 attributes, I mean all positive, negative, and ink dec, if they agree on these 2 things. But if you are merging 2 neurons which are green in color, then from the incoming side, you should retain the one which had the maximum weight. And the outgoing side, you should just sum these two weights into one. Okay. I'll give you an example later, but this is just the idea. Okay. If you are merging two neurons which are decrement kind, then you still take some of the outgoing, but you take the minimum of the incoming. Okay. So for two kinds of merges, you take the maximum of the incoming and the sum of the outgoing. For the other two kind of merges, you take the minimum of the incoming and the sum of the outgoing. Okay. This is our entire transformation. That is all that is there to this. Okay. So here is an example. Okay. So suppose we merge these two. Okay. So we merge these two into this merged neuron. This has been, it'll actually be one neuron. This is just to show that, this has been merged into one. So this entire outer thing.
You blow it up a little bit, please, because we can't see whether it is plus or minus.
Yeah, it is fine.
Yeah, okay.
Okay. So this has been merged into one neuron. Okay. And on the outgoing side, it doesn't matter what you merge. On the outgoing side, it is always going to be 5 plus 3 is equal to 8. Okay. It's only incidental that, here we are merging green and okay. So on the outgoing side, it's always going to be the sum of the outgoing edges. So this is 5, this is 3. So this will be 8. Okay. Next, tomorrow, if I merge this with this merged neuron with this neuron, then it will become 8 plus 4, 12. Okay. In fact, which is what can be seen here. If you merge all three, then this becomes 12. Is this fine? Okay. So on the outgoing side, it is clear. On the incoming side, let's see. So X1 was sending an edge of weight 1 to V1, and it was sending an edge of weight 4 to V2. Right? Now, when V1 and V2 have merged into one, X1 cannot be sending two edges to this merged thing, right? So X1 must pick one of them or somehow combine them into one. So they say that you pick the maximum one and then send it. So here, therefore, there is a 4 that is being sent. 4 is the maximum of 1 and 4. So therefore, there is a 4 that is being sent to this combination. If these were red, then 1 would have been sent. The minimum would have been sent. But these are green, so 4 is being sent. Okay. This is the abstraction. Is this clear? Any questions? Okay. No questions because, because we're just trying to do something. Okay. I mean, there's just a way of doing it right now. We are the ones who have to ask questions now. Then what happened to our original promise? Why should output become bigger by doing this exercise? Okay. Why should the output become bigger? If I merge these two, why should the output become bigger?
Because that was your original goal, correct?
That was my original goal, right? So we have to ask the questions that, okay, so why should the output become bigger? Okay. So here is the point. By picking the maximum one of these two is nothing but saying that, look, let me also treat this as 4. Okay. So by making this go from 1 to 4, I am only going to increase this, which is what I wanted to do. I wanted to increase the green ones because I know that they increase the output neurons. So that's why I picked the bigger one when I'm doing when I'm merging green neurons. If I was merging red neurons, if these were actually red, then I would have picked picked 1, right? Then I would have, instead of this 4, I would have picked 1. I would have picked the minimum one. So if I was merging red, I would have sent even lesser on this edge. Okay. That's why we are doing this whole thing of max of incoming and min of incoming, right? This whole exercise is to ensure that we are sending more to a green node and less to a red node. Okay. And because of this green-red marking, I don't have to worry about what happens at the output. The output is too far for me. I cannot worry about it. Okay. This marking gives me a way to bring this effect as close to the input as I can bring, so that I can decide in any layer that what should I do locally, what local change will give me a bigger output in the end. So this is just to bring it. This marking is just a way to eagerly see the effect on the output, to see the effect right now on the output. And that's why we have done this sort of a marking. Okay, so that I know what is to be done. Should I take the bigger one? Should I take maximum? Should I take minimum? And so on, right? So this is why we had done that marking, so that we could pick, when we are doing this sort of a merging, then we know, what edge weight to preserve on this common edge, right? Any questions till this point?
Any questions online?
No, sir.
Okay. Okay. So this is the abstraction part, right? This is all that is there to that abstraction part, right? Now I'll share the slides with you, and you can convince yourself that, I've written some formulas here, but these formulas, they're also there in the paper. This is how I've written them. R stands for ReLU. So this is trying to compute the output value of Y at this point. Okay, the output value of Y at this point is yeah. So yeah, sir, you had a question or a remark?
No. At this point, I mean, yeah. Why don't you go through that example if you were planning to? So then I'll ask my question. Okay, or I'll make a comment. Okay, were you planning to go through that those equations?
Correct. Yeah. I was planning to
Please go through that. Then I'll ask the question. I'll pose a question to the class. Okay.
Okay, sure. Yeah. Okay. So I'm just trying to say that, now I'm just trying to, at least for this example, I'm trying to show it to you that, what we have is indeed an abstraction, indeed a bigger output in the end, right? So what is the output here? What is the output that is being computed in this particular case, right? So what is the value that we get here? The value that we get here is 1 times x1 minus 2 times x2, right? So the value of v1 is x1 minus 2x2. Okay, not just this, ReLU applied on this, right? And the value of v2 is ReLU applied on 4 times x1 minus x2, right? And the value of v3 is 2 times x1 minus 3 times x2. Of course, ReLU applied on this. Okay, and the value of y is 5 times this value plus 3 times this value plus 4 times this value, right? Which is what I have written here. Okay, now if you do one level of merging, you can again write down this value like this. You can verify this for yourself that this is the value. 8 times the ReLU of this plus 4 times the ReLU of this, which is, okay, and then at this point. And then you can actually, when you go back, you can actually go and verify that, this value is actually bigger than this value, no matter what x1, x2 is. Okay, you can prove this mathematically that, this is bigger than or equal to this. The 12R of 4x1 minus x2 is bigger than or equal to 5R into this plus 3R into this plus 4R. So basically all that I'm trying to say that you can prove this, that this is bigger than this. Okay, yeah, that's what I was going to say, sir. Now you can pose your question.
Yeah, my question is, I mean, my comment, okay, and kind of a question. Of course, the authors of this paper in this approach, they choose to construct the over approximation by doing summation of the weights on the output edges and taking either a max or a min of all the of all the weights on the incoming edges, depending upon whether it is a green or a pink. My question is that, I mean, that certainly guarantees, as Madhukar in this example has shown, that it is what you get is more. Okay, So it's an over approximation for that property of that kind y less than or equal to c. Is this the only way to do? I mean, can you do, obviously taking a max and a sum is a safe way to get a safe over approximation, but you want to try and get as tight an over approximation also. So my question, I'm leaving the thought out to you. Is there a better way? Is there a better way than, by better, I mean just as simple to compete, to construct the over approximation, but a more precise. For example, computing the max, if the difference in the weight on the incoming edges is large, okay, and then you take a max or a min, I mean, it affects the precision, correct?
Correct.
Of your thing. So there could be better ways. I mean, my question I'm raising is, are there better ways? I have no clear answer for this, okay? But there could be. Now, especially if you have more information on about certain things. Now, one of the things that in abstract interpretation that you guys are already doing is, let's suppose that you somehow are able to compute bounds on the values of the nodes, okay, of all the internal nodes. Can you use that somehow to come up with a construction process that does not do max and sum, but something better? Okay, I don't know. Maybe they've already looked at this thing. I don't know. But that is a question that I want you guys to think about. Okay, and that could be interesting.
So this question is worth looking at, right? So here we nicely said that, look, this, when we are merging, and this is what sir was saying, when we are merging, we take max of incoming and sum of outgoing and min of incoming. This is clear. This clearly works. But is this the only thing that works? Can we do something else? Can we have a different function than taking the maximum? Can we have a different thing than taking the sum? And that's the question that we want, something that works, right? That guarantee is what we want to guarantee.
Yeah. Now, there's, what's your name? Romit here says you can't, okay? But I claim that you can probably do. Okay, I don't know. That's why I qualified. Without any additional information, this is the easiest way. I mean, to construct. But I wonder if you had more information that through further addition analysis that you are able to infer. And as an example I'm putting out is, through abstract interpretation, you can propagate bounds on all the values. Maybe you can, the question is, can you do better? I don't know. Maybe you're right. Maybe this is the best that you could do. I don't know. Okay. But that's just a question. Yeah.
Correct. Yeah. So, I mean, a different way of, I think, posing the question that sir is asking is that under what conditions can you do better? Are there certain conditions on inputs or certain conditions on some neurons? If you say that, this neuron can only have value between these values, then can we do better? So, I mean, there's also a one-line answer that no, without anything extra, this cannot be improved. But with something extra, can it be improved? And what is the least extra that you need in order to improve this? Is that what you were asking, sir?
Yeah, I think so. Yeah. I think this is a good point to stop, Madhukar.
Yeah. Yes, sir.
I think there are still a few things you would have to complete. The example.
Yeah, I'll complete.
Show how exactly, I mean, the refinement process and so on.
Yeah.
I mean, how you split. Okay.
Yeah.
So let's reserve that for, Thursday.
Yeah,
okay. Because, I need to do a few things to gracefully stop this, the recording, etc. So that will take some time, and then I'll have to leave at 5 o'clock. Okay.
Yeah.
So you guys, I might give you some simple exercises, not for grades. Okay. That'll kind of force you to listen to this lecture for those that have not listened to it, and for you to think about it. Okay. So that, some small examples that you can work it through so that you will understand this construction process, better. And so you'll be better equipped when coming into next class. Yeah. Okay.
Yeah. And here is my email address in case.
Yeah. Thank you, Madhukar. And I'll, Thursday also, the lecture is at 3:30.
Yeah, sure.
Will that will not be an issue for you, correct?
No, I'll be able to manage.
Okay. Thank you very much. Yeah.
Thanks a lot, sir. Yeah. Thanks, guys.
Can you go and then tell them that?
Could you maybe ask him to go a bit faster? Like, because just he didn't when he's explaining, he's just repeating himself.
We don't mind it being. Okay, the other one is.
That's the other one. But I think there were a few things because he has not listened to all the lectures that I have done. So they would have to do that. I think one comment, Madhukar,
The recording